Already have a grader, and we already talked about it, and he's going to use Canvas to submit your homework grades. If you submit it there, he will grade on Canvas and put comments. If you do by paper, he'll grade on the paper and put the grade on Canvas. All right, so look for that. And also the answer to homework 1, I made it. It's already on Canvas, but not open yet. Tomorrow it will automatically open. It's set to be open 8 a.m. tomorrow morning. Okay, question?
You want us to put this on your desk right now?
Before you leave? Yeah. And if you shall forget, you always have the option of scan it and put it on Canvas. Yeah, but don't forget. I'm not saying you should. Okay. So, how was the homework? Is it okay? Mm-hmm. All right. Okay, so what we will talk about today, we will go through a few examples of setting up linear programming models from word problems. Okay, and towards the end, I think in the other class I finished, and then we started a little bit on chapter 3. So, okay, another thing I forgot to say is homework for the second homework, it's already on Canvas. If you can't wait, you can start doing that. It's due next Tuesday. I typesetted it, and some problems are from the textbook, some are from other textbooks. My question will be, for you will be, have we bought the textbooks? Do we have it? I give you 2 weeks of cushion. I typeset all the homework problems. After that, I will refer to problem what from where from the textbook. Is that fair? Okay, so get it. You have 1 more week or a half to get the. So the book has a large collection of examples and homework problems, so it will be very useful to have. Okay, so with all the homework problems provided in the textbook, it doesn't make sense for me to search around and get other problems. It's redundant effort. Okay. All right, so talking about modeling today, so we will take an example. This is a complicated production example. Now, this one is taken from the textbook. It has a pretty lengthy, wordy part talking about the situation in real life. So I would not put everything on the board. I would explain to you and highlight information on the board. You want all the words? Read the textbook. Okay. So, so in some kind of a manufacturer, you are a manufacturer, and you are supposed to make product. So we will be producing 2 products. Okay, so I will label them as P1, P2. Is that okay? So 2 different types. Okay, and then of course you need to use raw material, and some other resources. So here are the list of resources. You have raw material, so I have 2 types. Okay, can I label them as A and B? Okay, let's call it material A and material B. Is that okay? So I have 2 types. And then, of course, plus labor. You need workers to work for you. And then in your factory, what you have, so it's an industrialized process, you have some processors. So you also have 4 processors that you can use to produce these 2 products. Okay, so the processes, they work in this way. So each processor would require certain amount of labor. So the workers will have to tend to this machine, whatever, and it will use raw material A and B as well, and then it can produce product P1 and P2 at a certain rate, okay, for each of these processes. So this information, I'm going to put it in a table. Okay, so let's put that. I have a tabular information for the following. So here are the different processors. So I have 4 of them. I call them 1, 2, 3, 4. Okay, and then each takes some labor. Okay, so let's talk about weekly production. So these are, or everything is per week. Okay, what's happening in a week? Okay, weekly, okay, process, whatever. So labor, so process 1 needs 20 hours of labor, hour per person, that's the labor, and then 30 for 2, 10 for that, 25. So each one needs workers to take care of it, and then each one will use the material A and B at a certain rate. So let's put that up. So let's say pound. The units are pounds here for the material. Okay. So these are numbers. So what do I have? 160, 100, 200, 75, and then 30, 35, 60, 80. So that's how much they use as resource. And then at the same time, each processor can produce the product. Okay? So how much they can produce, P1 and P2 of each product using these resources are also listed here on the table. So processor 1, with all that much labor, that much material from A and B, it can make 35 of P1 and 55 of P2. Is it clear, this information I'm giving? Okay, then I'll fill the rest. So for process 2, with this resource, it can produce 45 of product 1 and 42 of product 2. Okay? And then process 3, for some reason, it only makes product 1. Okay? And process 4, okay, for some reason, it only makes product 2. Okay? So that's the information we have in this tabular form. It ends right here, right now. And then, I will add constraints at the lower part. Okay. And then we have other constraints. Okay. So there is a production requirement Okay, so every week you have to produce at least certain number of product 1 and 2, let's say 2100 of P1 and 1800 of P2. So there's the minimum requirement of how much you have to produce, okay? And also, you have limited amount of resources. Okay, so let's list our resource. So what do I have? So for material A and B, I have limited access. So maximum amount of material A, so maximum amount of that is 4 tons, and let's just put it into the same unit. So it's 8,000 pounds, and MB also, I have only 2 tons of it, which let's say is 400 pounds. Let's use the same unit, okay? And then I hire a bunch of workers to work for me. They are my employee. They are paid with fixed salary. No matter how much they work, as long as I don't exceed the maximum allowed working load for them. Okay, so I do have a max labor. So I have maybe let's say so many workers, and they can work for me maximum 1,000 hours per week. Okay, If they work less, I pay them the same fixed salary. Is that clear? Okay. And then I also have price for the material. So, okay, so this, let's say, fixed salary on that. That one I cannot change. Then I have price for material. Okay, for material A, this is somewhat cheaper material, so $3 per pound. And material B would be $7 per pound. Is it clear, the setting? Okay? Anything, any questions? I explained all? Okay, so now here comes the question. So you are the manager for this factory, and here's the question. So how should you use these 4 processes in a way that you meet the production requirement and within the limitation of your resource, okay? But you only care about meeting those standards, and at the same time, you want to pay less for the raw material. Is that clear? So let me write out. What do I want? How to use the 4 processors to meet all constraints that we have there, and minimize the cost of material. So we want to set up a linear programming problem for that. Is it clear, the setting? Okay? All right. Okay, so LP model. So let's declare our variables. So what are the objects that I can control to change the cost function? What are my choices here? Any suggestions? What should I use as my variables? Yeah? Say it louder, I didn't get. So you want to declare these 3 as my variable. How many hours of labor? How much of each of these? And then how do you know how much work does each processor do? As a manager, what would you need to really know? Can you rethink? Yeah, so usually it's in the question that's asking, it is asking how to use the 4 processors, right? So I can make a choice that I can use 10 hours of this, 20 hours of this, 15 hours of this, 2 hours of this. And then once this is given, I would know how much labor will be involved. Does that make sense? So usually ask how to. That usually is where you do your variable. All right? Okay, so we have 4 processes. Then I need to declare 4 variables. So x1, x2, x3, x4. Okay? So let me write it here. So how much I use for processor 1. So here's my variable, actually, x, all these x's. I'll put it as what I declare as my variable. Okay, so these will be number of hours, okay, per week. Okay, it's weekly of processor 1, 2, 3, 4, respectively. Is that right? So once these are determined, and then the rest is all determined, basically. Is that right? Okay. So now, in order to figure out the constraints, so let's put all these constraint information on this table, so you will have everything when you look at this table. Then I don't need to go back to those words. So let's put these back. It's nice to have. So let's come back to the table. So for the resource, I have max amount allowed. Okay, so labor, I have maximum 1,000 hours. Material A, 8,000. Material B, 4,000. Right? That's the maximum I can have. And it also have, for the production, I have to reach at least, so that's the minimum amount that I must meet for A, for production 1 and for production 2. So this is also the minimum amount I must meet. Is that okay? And then I have a price for all the material, right? I can put it here. So for the labor, this is fixed, so I cannot change it. That's nothing to do here. For material A, what did we say? $3 per pound, and that's $7 per pound. So now you have everything on the table. Then you can just go to the table when you want informations. Okay. Okay, with all this set up, now let's see. I need to minimize the cost. So your problem will be minimize the cost of material. Okay, so let's set up this cost function. So z equals to a function depending on my variables. So how do I figure out this cost function? I have two materials, A and B. Is that right? Can we nail down how much will it cost for me by using material A? Let's look at material A. Material A has a price tag. In order to compute its cost, I need first to find out the total amount of material A that I will be using, right? Then I can multiply it by the price and I know how much I have to pay. So we need to nail down the total amount of material A that will be used. How do I find that out in this table? Yeah.
3 times like the quantity of X minus X2.
The total amount of material A that I will be using. How do you find that out?
Under material A, the vertical.
So I need to add them up vertically, as we have done. So before I add up, what do I need to do? This has to be multiplied with x1. So I will multiply x1 all over here, x2 here, x3 here, x4 here. Then I can start to add them up vertically. Is that right? Is it clear to everyone? So the total amount of material A will be this times x1, this times x2, this times x3, this times x4, and I add this up. Okay? So I will have, let me see, 160 x1, 100 x2, 200 x3, 75 x4. So in the bracket, this is the total amount of material A that will be used. So how much will that cost me? Multiply by the price. Is that right? Is that clear? So for material B, now it's the same, isn't right? The same process. So does anyone want to tell me how do I figure this out for material B? What will be the total amount of material B that I would use? I use this column. Is that right? What should I put here? Tell me the first term. 30x1. And then you just keep going. Is that right? 35 x2. And you have 60 x3. And you have 80 x4. And then that shall be multiplied by the price, which is $7 per pound. Is that right? Okay. Is that clear? This is the cost of the material. Okay. So now I don't know why I do this, but it itches me. I need to collect like terms and write it out. So allow me to do that. So 690. That's the x1 if I add them up, and 545 x2. 1070 x3, 785 x4. Okay, so that's my cost function, which I want to minimize. Okay, so this is a minimization problem. Minimize that. Okay, so I have a bunch of subject to. I have many constraints. Seems like this is a rather complicated problem. So I have constraints coming from two things. One is I need to meet the minimum production requirement, and I cannot exceed my resource. Is that right? So let's look at the production part. It says I need to produce at least that many of product 1 and that many of product 2. How do I do that? So the question first will be, with these choices as my variable, how many of P1 will I produce in this table? We've done this so many times already now. So how would I find out the number of P1 that I will produce? I add this up, right? After I multiply x1, x2, x3, x4, I add this up, right? So, okay. So let's do now product for P1. I have the minimum requirement, so I have 35 x1 plus 45 x2 plus 70 x3. And the last one is 0. I'm not going to take it. So what will be my constraint? Yeah, question? Huh?
The x3 variable for the first equation.
Did I copy a wrong number?
It's 600 plus 4.
Which one?
Correct.
This one? x3.
When you combine the terms.
200.
Where it says 1070, it's 10. It should be.
This is wrong.
Yeah, it should be
20.
1020.
Thank you. Yeah. So I should not have done that. I should just let it be, right? Okay. Thank you. All right, so back to my question. So how do I write out this constraint? I computed the total number of product 1 I would produce, and that has to be bigger than that, right? So bigger than, equal to 2100. Is that clear to everyone? Okay. So just keep your head cool and just sort everything out, and that's it, actually. Each step is not confusing, but you just have to take several steps, okay? So what about product 2? What do you say? I would add this up, and it has to be bigger than that. Is that right? It's just numbers now. Okay, so 55 x1 plus 42 x2 plus, x3 I skip because it's 0, so 90 x4 shall be bigger than 1800. Okay, so that's the production requirement. Then I have the requirement from the limited resource. Okay, material A, material B, and labor. They all give me constraints. So how do I find out the constraint for material A? we actually did part of the work because we know this is the total amount of material A that will be needed. Is that right? And that cannot exceed 8,000. Is that clear? Right, so just, okay, it's next to me. Let me copy 160 x1 plus 100 x2 plus 200 x3 plus 75 x4 shall be less than 8,000. Okay? And then we know this will be the amount of material B. Is that right? So I will have 30 x1 plus 35 x2 plus 60 x3 plus 80 x4 shall be less than 4,000. Is that clear? And then I have a similar thing for the labor. If I add up the total amount of labor hours per person, it shall be less than 1,000. Okay, so let me do that. So 20 x1 plus 30 x2 plus 10 x3 plus 25 x4 shall be less than 1,000. Okay, so that's the second set of the constraint. And always, always in this class, I shall never forget to add, that comes to every problem, the non-negativity. Is that right? All the variables are naturally taking non-negative values. I cannot use negative amount of process one and undo some products, right? That's not possible. Okay. Is that okay? So seems to be a rather complicated situation, but you know, every step is elementary. That's what Sherlock says. Okay, so let's make it a bit more complicated. So, okay, so you are the manager of this factory. You did some computation. You set up this problem. Say you know how to use the simplex method. You solved it, and you have a solution. And you're not happy. You think you're paying too much. So you have the following question: is there something I can do to maybe it will be more beneficial? But you don't know. So one thing that you can play with will be, okay, I have this amount of workers. They can work for me maximum 1,000 hours. What if I ask them to work overtime and I pay them extra salary? Would that be more beneficial for me or not? Is it clear that's the question? Okay, so here's the question. So I allow overtime, just to make it more complicated. Would this be more beneficial? So I have to put out my terms. So overtime will be, there are laws against really very high overtime. Let's say I can add maximum 200 hours of overtime per week for all my workers combined, okay? And I have to pay an additional salary. I'll put it here. So what do I pay? Let's say my offer is $30 per hour. Okay. So what will be the corresponding linear programming problem? If I set it up, then I can solve it and I can figure out which option is better for me. Is that right? Okay. So what will be the LP problem? So okay, so how should we handle this extra, you have extra freedom you can choose and extra control that you can decide. Is that right? So this is somewhat similar to the problem we had last time, where we had choice of buying material. If we buy too much, we pay a somewhat higher price, and we can decide if we want to pay that extra high price or not. Do we see the similarity here? You can easily think those labors are changed into some type of raw material. Comes with a fixed price if it's less than a certain amount, and more if you buy more. Similar, right? So we would introduce a new variable to deal with that. Okay, so let's call it x5, the variable number 5. What would that be? Well, that will be exactly the amount of overtime. So number of hours of overtime that I will allowed. Okay? So pay attention, the wording, it's the hours of overtime. So this guy x5 here is never negative number. Okay? So it's bigger than 0. And I also know that I cannot give more than 200 hours. So immediately this variable has some constraints on it. Okay. All right, so how would I change my problem? Based on the previous one that I already set up, with this new situation, how could I change? So what will be the new cost function? So let me write, the cost function will be z equals to, let's call it g, depending on all the previous variable, and it also depends on the new one that I introduced, right? Okay, so now I have two costs. One is the raw material A and B. They will cost me, which is computed in the same way, so I'll just copy. So this f is just this f here. Okay, so I'll copy. I based my new model on the previous one. So that's the cost of raw material. But then I have potential cost of overtime payment. Is that right? So how should I modify my cost function? What do I need to add on top of that? It has an additional term. Any suggestion? Yes?
30 times x5.
Yeah. Is it clear to everyone? If I allow that many hours of overtime, each one I pay 30, that's what I will have to pay. Is that right? So my cost function is somewhat modified. Okay. What about the constraint? So I still need to minimize my cost, subject to. Now I have somewhat different constraint. Okay, so let's look at production requirement. Do you think those will be changed in this new situation? So the constraints, let's say, to meet the production requirement of product 1 and 2, do you think I need to modify my constraint here? Yes or no? If I use these numbers of hours for each process, the number of product 1 I will be producing is the same formula. Is that right? It's not changed. So is for product number 2. Is that right? So these remain the same. I don't have to change anything about that. Okay? Okay, so then let's check the resource. So for the resource, I did not make any change in material A or material B. They are the same price. They still have the same maximum amount. So these constraints are the same as the previous situation. So the only thing is different now is the labor, because I allow overtime, so, and I pay, so there is some change there. Okay, so let's list in detail the change in labor. So the total amount of hours I would have is still the same. So let me put it out. 20 x1, that's the hour of labor I need to run these processors. Okay, so this is hour of labors needed to run these processors. So this shall be less than equal to, what should I put on the right-hand side? So the previous one is just less than 1,000. And now I allow x5 hours of overtime. What would I put on the right-hand side? Is it clear to everybody? That's 1,000, and I allow overtime. Is that right? So you think like this. If no overtime occurs, x5 is 0, then it's the same situation as before. The total hour shall be less than equal to 1,000. And if certain amount of overtime should occur, and then this would add up to be equal to this plus a positive x5. But that's included in less than equal to. Is that right? Okay. And then I also have further constraint on x5 because total amount of overtime I can take is 200. So I have 2 constraints for the labor. Okay. And then also I have non-negativity, x1, x2, x3, x4. And I need to include x5 here as well. All of these shall be non-negative. Is that okay? Question? Yeah?
Why instead of having, because you have 1,000 plus 200, or does it have to be 1,000 plus x5?
Because I need to keep track of how much I pay for the overtime. I do not want to use all 200 hours of overtime. I want to find out up to 200 hours of overtime, what is the good number of overtime that I use that will minimize my cost. Right? That's why we introduce this x5. So the total amount of overtime is less than 200. But I don't want to use 200. I want to use whatever is optimal for me. So then I define this, that's the amount of the overtime. Right. So in the end, the right-hand side will be less than 1,000 plus 200. It will be. But it might not be equal to 1,200. Does that answer your question? You still look confused? Okay. Yeah. So it's kind of a standard treatment of this type of problem that when you go over a certain amount, the price is different. Then you have to keep track of how much you go over a certain amount. This is a standard treatment to handle that. Yeah. It does feel a bit weird. Yeah, I agree. Yeah. So, any more questions? Are we okay? So this is as complicated as it could get. I will not give you more complicated problems than this one to deal with. Okay, so if you can handle something like this, we're good. All right? Okay. One more type of problem that's in chapter 2.4. I will give one like general example. This is called the transportation problem or transportation model. So it's a little bit different from all the others we have seen, so let's talk about it. So the setting is the following. So you have some goods located in some location, let's say 2 different storage places, okay, and different storage places. And then you want to transport them to other location, let's say shops that will sell them. Okay, each shop wants certain amount from your storage, so you need to set up some kind of a transportation schedule. So from warehouse number 1, how much shall go to store 1, store 2, store 3? You have to decide what to do. And then maybe the distance from the warehouse to each store are different, which incurs different cost for transportation, or maybe the roads are bad or whatever, and you want to minimize your cost. Is that clear? So let me set it up. Okay, so I have goods at location AI, certain number of them. Okay, I need to transport to location BJ. I have a bunch of them. Okay, and the cost from transportation cost from AI to BJ usually is given, so you would know how expensive it will be. And then the goal of all these problems is find a schedule to minimize the cost. Okay, is that clear? Okay, well, I'll give a concrete example. So, okay, so let me clean it up here. Well, not so concrete, kind of a concrete. Okay, so kind of a generic, rather general example. Let's give certain number of locations. So let's say I have 2 locations, A1, A2, okay, 2 storage, say. And then I have some goods that's being stored there. Let's say at A1, I have 200 units stored there, and the A2, I have 300 units of some stuff. Okay? And I want to distribute them. So distribute them to, let's say, 3 different stores. Let's call them B1, B2, and B3. And each of them wants certain number of units of my stuff. So the distribution is following. So B1 wants 100 units. B2 wants 200 units. And B3 wants also 200 units. So your job is to redistribute these from A1, A2 to all the B1, B2, B3 locations. Is that okay? Okay. And now, in this type of transportation problem, usually is the case that how much you have here will be total amount, will equal to the total amount of what you have to distribute. So everything will be distributed. Okay? So put this as a note. I would have A1 plus A2 equals to B1, B2, and B3 adding up. Okay, that will be usually the situation. Okay, and then I have the transportation cost. Okay, this shall probably is best listed in a table. So let me write from AI to BJ. There are 6 numbers here, so let's list it in a tabular form. So this will be from A1, A2, to B1, B2, B3. I will fill this table according to what information I have. So let's just throw in some numbers. 1, 1, 1, 2, 1, 3, 21, 22, 23. Okay? So it's most expensive to ship from A2 to B3. It's the cheapest. The cheapest one is to ship from A1 to B1. Okay, some number. Okay. Okay. So how do I set up the schedule? So the schedule will have to contain information, pretty detailed information, isn't it? I need to know how much from AI will be shipped to BJ. Is that right? So let's see how we can set up schedule. Okay, so let me say Xij will be the units shipped from AI to BJ. I set up that schedule. Okay? So I could do it in a tabular form, which will give me clearer idea. So A1, A2 from that. So what I put is cost. Okay? No, not cost. Schedule units. Sorry. This is the cost table. 2, B1, B2, B3. So I call this Xij, then this guy will be X11. Is that right? Xij. And this will be X12, X13, right? So X21, X22, X23. Is that clear? So these 6 numbers, I need to decide what to put in there. Is that clear? Right, okay. Okay, so leave a little bit space because I'll go back to this table. So now, first step, let's figure out what will be the cost function, okay, which I want to minimize. So what will be the cost? So it's a function now, z equals to a function f, which depends on all those 6 x's. Is that right? I'll just write it like this, collection of xij. You could fill in this 6x if you want. It means it depends on all of them. So how do I figure out this cost? Any idea? To transport x11 unit from A1 to B1, how much would that cost me? So how much would that cost to ship x11 unit from A1 to B1? The cost is given here, is that right? That's the price to ship each unit, right? So what would that be? That's for each unit. I'm shipping x11 units. So this will be 11 times x11. Is that right? That's the important one. You understood the first one. The rest is all the same. So 11 x11 will be the cost to ship that. So now what about this one? To ship x12 unit from A1 to B2, how much will that cost me? 12 times that. Okay. And this one will be multiplied by 13. Is that clear? Then I have to finish, I have to go through the table, right? So you see that I would take this table and put it on top of this table, and the number in the same position, I will have to multiply them. Then I add all of them up. Is that clear? Okay, so let me finish. So I have 21 x21, 22 x22, 23 x23. That's the cost function to minimize. Okay? All right. Okay, what's the constraint? What will be my constraint? Okay, so following this schedule, I am shipping that many from A1 to B1, that many from A1 to B2, and that many from A1 to B3. So how many will be shipped from A1? How do I find out that number? How many units will I be shipping from A1? Add these up, is that right? And this, if I add up, I must reach the number of units that I have in A1 because they all need to be shipped. Do we see? That's a constraint. And what about from A2? I need to ship all of them. So what will be the total unit being shipped from A2? We'll be adding up this row. Is that clear? And that has to add up exactly to 300 units. Okay, so that's my constraint. So let's write it. From A1, I ship from A1. So X11, X12, X13 add up should be exactly 200. And from A2, so X21, X22, X23 equals to 300. That must met because that's the constraint. Okay. Now, according to this schedule, so how many units will B1 receive? How do I figure that out? I would add up vertically, isn't that right? I add these two up, that will be how many B1 would receive. And how many does B1 need? 100. Is that right? And B2 needs 200, and B3 needs 200. So I add these up. They must meet these three numbers. Okay, so that's from, and now 2, B1, B2, B3. Okay. So I will have X11 plus X21 is 100, X12, X22, 200, X13, X23 is 200. These 5 constraints. And always the non-negativity. Constraint. All of these have to be non-negative. Yeah. Is that clear? So actually you can see that out of these 5 constraints, one of them is redundant if I have this to start with. Is that right? If I put up 4 of them, the last one is automatically satisfied because they have to all add up, all be distributed exactly. Okay, but okay, let that be. Right. Okay, so the new thing in this example is that we see that now constraints can be equal sign. Okay, so that's a new thing. We haven't seen this in other examples. So constraints can be equations, not inequalities. inequalities. Earlier we have seen bigger than equal to, less than equal to, and now we see equal to. Okay, so in this course, just a remark, in this course we will be handling constraints of less than equal to, bigger than, equal to. That always contains the equal sign as part of it. Because in practice, the strictly less than or strictly bigger than constraints are not practical. Usually say minimum requirement must met. Meeting that is allowed, right? So usually you never end up with really less than, strictly less than sign. And mathematically, if your constraint is strictly less than or strictly bigger than, then the feasible region will be an open set mathematically. It will not include the boundary. And that causes a lot of trouble in analysis, and we don't want to get into there. Okay, so we close the boundary, it's contained. It's okay? So bigger than. So we only use those constraints. Okay. Are we okay? Transportation problem? You might get some of these to practice with. Okay, so we see that. Let's just take a look back at all the problems we have set up. We have minimization, maximization, both are possible. And we have constraints being bigger than equal to, less than equal to, all combinations. It seems like there is a huge variety of different types of linear programming that we are looking at, right? That's not very nice, isn't it? I would like to have a standard form that I can use to study. So I will give you a good news, so don't worry. All these can be rewritten into a standard form. So all these problems can be transposed or rewritten into a standard form. Okay, so let's talk about that first. What do I mean by a standard linear programming problem, and how do I change any of the other problems into that? If that is settled, then I just need to study the standard form. Is that clear? Okay, that's our approach. So let's put that. So that goes into chapter 3. I will tell you standard form of linear programming. Okay, so let's give this definition as a definition. What do I mean by a standard form? Okay, so it's the problem that I will set up now. So minimize the function. The function takes the following form: z equals to c1x1, c2x2, all the way to cn xn minus a constant z0 subject to bunch of constraints a11 x1 all the way to a1 n x1 equals to b1, and goes all the way down to a m1 x1 plus a m n x n equals to b m. Okay, and also the further non-negativity constraints. So xi's are bigger than 0, I from 1 to n. So that is the standard form. Okay, so it's the transportation problem falls into this form, right? The constraints are given as equations, not inequalities. Okay, and you have a function to minimize. We are not considering maximizing problem. We only look at minimization problems. Okay, so let me specify here. X are the variables, and the others are constants. So here, what do we have? All the A, I, J's, and all the C, J's, and the B, I's. Is that right? Bless you. I is from 1 to m. J is from 1 to n. All these coefficients that I put here, and also the z0 I put there, they are given. They are constants, just numbers. Okay. So you will see this could be written in a much more compact way if you allow me to use matrix times vector. Do we see that? That will come later. Okay. So, and these m n, they are two integers. They're not necessarily equal to each other, because if you're equal to each other, you can solve this. So usually the number of unknown is much bigger than the number of the equations. Okay, so you have a region, feasible region out of that. Okay, so we will look at a few techniques or tricks, whatever you want to call, to show that any other problems can be rewritten into this standard form. So, okay, so let me put this up. So I also would have n shall be bigger than m. Normally, they're not the same. Okay, so I have one remark. One can transform all the LP problems into this standard form. Okay. So let's look at the first thing. Here we consider only a minimization problem. What if you have a maximization problem? How can you handle that? How do you transform it? Okay, so technique one or trick one, say, let's say if I want to maximize some function, z equals to f. Let's just put in two variables. Once you understand that it's the same, how do I change it into an equivalent minimization problem? So I say this is equivalent to a minimization problem. Minimize z equals to what? How can I do that? What can I do to this function so that the maximum here will be the minimum to what I will write down? Any idea?
Put a negative on the inside?
Yeah, it's very, very simple. If I look at the negative of this, the maximum here will be the minimum. Is that right? You flip the whole thing. The tallest one now becomes the lowest one. Is that right? That's all. Okay, so now any maximization problem can be changed into minimization problem. So that is taken care of. Now we need to talk about the constraints. In the standard form, the constraints are all equal sign, right? And in our model, we have seen lots of less than, bigger than, equal to sign. How do you do that? Okay, so let's look at a few tricks for dealing with different types of constraints. So let me take an example. Let's say I have the problem, minimize z equals to x1 plus 2x2 plus 3x3 subject to the following: x1 plus x2 plus x3 less than 10, x1 minus x2 bigger than 5, x1, x2 bigger than 0. It's a linear program, right? I minimize some linear function with all linear constraints. But this is not in the standard form because my constraints are using inequality. So, okay, so how can I change it into equality? Okay. Think about it. Okay, I'll come from here. Let's do this. Any suggestions? How can I change an inequality sign into equal sign as my constraint? I need to make it more complicated to accommodate that, right? So, any suggestion? The hint is hiding here. Oh, I forgot x3, sorry. For all these linear programming problems in the standard form, also all the problem we run into, we have this non-negativity constraint for all the variables. Is that right? Everything we are seeking has to be non-negative. Okay? So this is actually something we will take advantage of in this manipulation. So let me state something. Tell me if you agree. Let's say, let's say if I have a constraint, what should I write? Let's say x less than equal to b. I can rewrite it in another way. So x is positive. I know under further constraint, I know always that's a non-negative quantity. X is less than b, less than equal to b, which means I could add to x some non-negative quantity such that x could reach the value of b. Is that right? So think about that. I say this is equivalent to the following. I add some additional thing to x, let's call it x tilde, so it can reach the value b. And I know this is some non-negative quantity I can add on top of x. Do we agree on that? Think about it. Is that okay? Do we all see? So the less than equal to constraint now can be rewritten into an equal sign by introducing a new variable which shall be non-negative. Is that okay? So that's one. And I can handle the other one in the same way. Let's say the other constraint, let's say I have a constraint x shall be bigger than or equal to b. Okay, I say this is equivalent to, so what should I do? I know that x is bigger than b. Which means I can subtract from x some non-negative amount so x can equal to b. Is that right? So I will have x minus x bar can equal to b for some amount x bar which is non-negative. Is that clear? And these are the technique or trick, whatever, we will be using to deal with these inequality sign constraints. And I will change them into equal signs. So each inequality will be changed into an equal sign by introducing a new variable. So for this problem, I will have to introduce two new variables. I will call them x4 for this equation, inequality, and x5 for that one. Okay, so back to the problem. How do I handle it? We're almost there. So I will introduce two new variables, x4 for the first equation, x5 for the second equation. Okay, so now my constraint will be the following. So I will have all the non-negativity constraints. That's very important. These are bigger than equal to 0. And then for the first one, I have less than equal sign, and I will add an x4 onto it and change it into equal. Is that clear? That's all there is. So okay, so x1 plus x2 plus x3, I will be adding an x4. This is new, and this equals to 10 plus x4 is bigger than 0. Then I take care of it. Okay? Is it clear? Okay. So for the second equation, I have bigger than or equal sign, and then I introduce x5 to handle that. I will need to subtract this x5 to change it into an equal sign. Is that right? Okay, so x1 minus x2, I will have negative x5. So that's a new thing. That shall equal to 5. And then x5 is non-negative. Now, this is in the standard form. Is that okay? It's just that trick. Okay. You could rewrite it again to check it exactly matches the standard form. Okay, so let me give you the name. So these two variables that I introduced there, these new variables, what do they mean? They actually tell you something of this problem. x4, x5 will tell you how much this equal sign is not measured inwards the feasible region. Is that right? So the constraint says less than or equal to. And I put a x4 to it. So if x4 shall be strictly positive, then that means I will have less than sign. The amount of x4 tells me how far away this condition is from the equal condition. Okay? And you know our observation that the maximum and the minimum is obtained at the corner on the boundary, usually where the constraints are equal, right? So how far away we are from that, that's kind of important. So they carry a name. These are called slack variables. Okay? So they measure the slack or surplus of the original constraint with the inequality. Okay? All right. Then there are other tricks we need to learn that will come next time. So, any questions? Are we okay? All right, then see you on Thursday.